Hello. In this video I want to do a small demo of the distributed optimization thing that I showed in the last video, as 100% of the comments requested that. I had one comment, so 1 out of 1 suggested to make a coding video. So I thought, let's go. Alright. Let's start with importing some libraries that I'm going to use. So I'm going to use NumPy. I'm going to use something from SciPy as well. And then for the plots, I'm going to use matplotlib by plot. Okay, so essentially what we want to implement is this distributed optimization algorithm where our objective function is a quadratic. So to keep things simple, we have an objective function which is basically ax minus b, a being a matrix, x being a vector, b being a vector, and then the L2 norm squared of this thing multiplied by 1/2. What I'm going to do is I'm going to generate A with a certain condition number. A is a matrix and it has a specific condition number that we will define. So for this, I'm going to use a little helper function, which I'm not really going to explain. It's just one way to generate a matrix with a particular condition number. So I'm just going to copy this from some code that I already have, but essentially what it does is it outputs this matrix A, where A is given with dimensions m times n and has a specific condition number that we're gonna define. So then the next thing is gonna be, let's define our objective function structure. Alright, so as I said, we're going to have a quadratic function. So basically, remember the distributed optimization setup. We have these fi's, and we're going to say that each of these fi's is some matrix ai times x minus this bi vector, and then the L2 norm squared of this guy. And this for basically all the particles or processors in our system. So again, distributed optimization, we have data or objective functions that are local to each of the nodes in our system. So each of the nodes can only access its own objective function, and collectively they want to minimize the sum of these things. So basically each of these objective functions is going to be defined by fi, and then the global objective is going to be to find the minimizer x that minimizes the sum of all these fi's. And as I showed in the last video, this basically is the same as saying that we want to find all the x1, not great notation, and a number of particles. Sum is1 up to, again, this n thing of the fi as a function of xi now, such that each xi is equal to xj for ij connected. So again, I'm not going to go into too much detail on this, but this was discussed in the previous video. But essentially, we want to minimize this sum. Each of the nodes devices, whatever, stores its own parameter estimate xi. X is the thing that we want to minimize for. So we can basically reformulate our problem in this way: find the xi's that minimize the sum such that they all agree on their value, so that all the parameters in our system, they have the same parameter value. All right, so let's define the objective function. Let me first define the A and B. So A, as I said, I'm going to generate it with a certain condition number, and B, I'm going to generate from a multivariate normal, or maybe IID normal. So let's define something called the quadratic, which is going to be, let me also specify what I mean with all these inputs. So D is the dimensionality. So basically each xi is going to be in, if I write it in LaTeX notation, like this. So each xi is d-dimensional. Number of particles is basically the number of nodes, devices, again, whatever you want to call it. I sometimes call it particles because I'm used to it. And then the condition number is the condition number of the matrix A. So I have to generate an A that is going to be of size D times the number of nodes in our system by D. Because I basically want to have this matrix A be consisting of these block matrices of D by D, where each of those block matrices is the AI that we have in each of our local objective functions. So I'm going to define the big matrix A to be first just zeros, and then I'm going to fill it up with some stuff. So D times the number of nodes, particles by D, and then B is going to be the same, except it's going to be a very long vector, where each of the sub parts of the vector is going to be the BI. So I'm going to define this guy as, again, D by number of particles by 1. I think that should be fine. And now what I'm going to do is I'm going to go and define all of these local FIs, or well, not the FIs for now, but the local AIs and BIs. So I'm going to loop over all the particles, so in range number of particles. And then I'm going to say that the PS subcomponent of the matrix, so PS times D until PS plus 1 times D, and select all the, so I'm going to select the PS times D row up to PS plus 1 times D row, so it's going to D rows, and then I'm going to select all the columns, and this guy is going to be sampled from this function. So I'm going to sample it with a certain condition number. This should be D, this should be D. So basically, again, each AI is a matrix D by D with a certain condition number that we're going to specify. And then for B, I'm going to do something similar, except I'm going to sample it from a normal distribution. So I'm going to use NumPy's normal thing, 0, 1, and then of size D1. I think this should be correct, this D1 thing. Let's see. And then this function is just going to return A and B. So it's basically just going to return the inputs for each of our loss functions. And then I'm also going to define the total loss. Let's call it evaluate the loss. Again, nr particles and x. So basically this function, what I wanted to do is I wanted to evaluate this sum over all our nodes / particles of each of the FIs. So the way I'm going to do it is not very efficient, but I'm just going to use a for loop because that is easy. So then I'm going to do, again, for particle in range number of particles, I'm going to increment this loss by computing each of those local losses. So basically this thing. Sorry. So I'm gonna have to compute the L2 norm squared of AIX minus BI. So I'm gonna use NumPy norm, and then basically again, same thing as what we did before. I'm gonna select each of those AIs. I'm gonna multiply them by X. And I'm gonna subtract the BI thing, so this guy. That makes sense. And in this case, since A is d by d, just so I don't forget, the X will have to be d by 1, I guess, because RB is also d by 1. Alright, cool. Okay, so let me first see if all of this even works. So let's define some of the parameters that we're going to use. So let's say we're going to have 10 nodes or 10 devices, particles, whatever. Let's say we're using a dimension of 5, so X is in R5. Let's say for now the condition number is 1. So let's start with generating the A and B, the big A and B matrices, which consist of the AI and BIs. So I'm going to use quadratic. What did we define? D and our parts cont. Oh. Okay. I think we should also be able to calculate the optimal solution of this thing using the least squares optimal solution, which should be something like this. ATA inverse times AT times B, I think, but you should check this yourself because I always make mistakes with these kind of things. And then let's also just evaluate the loss in this guy. X opt. Alright. I'm gonna check what this gives to make sure that this even works. So I'm gonna run this thing, which I called distributed. Oh, ooh, surprise, surprise, it doesn't work. Why? Ah, okay. Because I had the quadratic in a weird location. Okay, it gives something. So I hope that something is correct. Okay, so what we've done now is we have defined our A, again consisting of those AIs and BIs, and we have defined our loss function. So now, what should we do? Maybe we can define the graph. Okay. So just to also make sure we remember the dynamics that we're going to use for the optimization. Okay, so now let's go on to define the optimization algorithm that we will use. And remember that the distributed optimization algorithm was given by something like this. So basically our parameter, or the thing that we're interested in minimizing over, which in our case is this x, is going to be updated. So the x at time t plus 1 is going to be the x at time t minus the learning rate times the gradient. Well, let me write it in LaTeX notation, nabla f of I, because node xi only has access to fi, so it's going to compute the gradient of f of I, evaluated at xi at time t. Then we're going to have our interaction term, and our interaction term is basically how this node communicates with the other nodes in the system. So it's going to be this sum over the j's. I'm not going to write nr particles because I can't be bothered, so I'm just going to write n of a I j x j. Is it xj or xi? Xj minus xi. Here this epsilon is a kind of hyperparameter that controls how much focus we put on this interaction part. So basically what this thing says is that if the neighbors of xi have a higher value, then this contribution from this term is going to be positive, aka xi is going to increase. And if the neighbors of xi, so all these xj's that it's connected to, have a lower value, then this thing is going to be negative, aka the value of xi is going to decrease. So in this way, kind of, it tries to converge to whatever the values of its neighbors are. And then I'm also going to add some noise. Am I going to add some noise? No, maybe I won't add noise for now. If you wanted to, you could just add like some sigma times the Brownian motion noise. But I think for now I won't do this. So if we want to define this, we first also need to define this aij. So I'm going to use two different structures of the interaction graph. So again, aij is basically defining with whom of the neighbors of xi is communicating, aka sending their parameter values. So I'm going to define a fully connected graph. The input is going to be the number of particles. So for the fully connected one, I basically want each xi to be communicating with all the other nodes in the system. And I'm going to not be very precise because I'm also going to say it's going to communicate with itself, which is weird, but whatever. If you remember from the previous video, we also briefly talked about whether or not A should be doubly stochastic, aka its rows and columns sum to 1. I'm going to say that it should be, so that's why I'm going to define this aij to be 1 over the number of particles, so that if we sum the rows and the columns, we're going to add up to 1. So basically, yes, aij is going to be 1 over the number of particles for all ij from 1 up to nr parts. And then the matrix itself, I'm going to call it intermat, is going to be a matrix of size nr parts divided by number of particles. So basically this is a matrix of only ones of size number of particles times number of particles, and then I'm dividing by number of particles. And then I'm going to return this guy. And the other graph that I'm going to define is going to be a circle graph, I think. So basically a graph where each of the nodes is connected to one of its neighboring nodes. So let's say node 1 is connected to 2, 2 to 3, 3 to 4, and so on. So you basically have a circle connectivity structure. Very unoriginally, I will call it circle graph. Ta-da! And then basically what this is going to look like is, as I said, this. So particle 1 is going to be connected to 2, and then 2 is going to be connected to 3, and so on. How am I going to define this? Let's say I first define an empty matrix of, again, number of particles by number of particles. And then, again, I'm just going to loop over all the particles. and I'm going to do it twice. This might not be the most efficient way of doing this, but I'm only using 10 particles, so it's fine. And then I'm going to define the value of aij to be 1 if the second loop index is going to be equal to the first plus 1, something like this, which will basically say that if this, so we start with 1 here, and only if the second iteration, second index is going to be 1 plus 1 is 2, we're going to give it a non-zero value, and otherwise I give it 0 values. And then I just need to make sure that the last node is connected to the first one again, because I want the graph to be fully connected, aka I want there to be a closed loop. So then we would say the last element and the first one are also connected. Let's see if this worked. Let's define the first graph to be the circle graph, and then the second graph to be the fully graph. And let's print them to be sure that it does something that is mildly correct. So the circle graph, I guess, looks fine. The first element is connected to the second is connected to the third, and so on. And the fully connected one, yeah, just has 1/10 in all the elements. So I think that's fine. All right, almost done. This always takes longer than I think it would. I was planning to do this in 15 minutes, which is not working. All right, so the final thing that we're gonna have to do is obviously implement the optimization algorithm itself, which I'm gonna call distributed optimizer. What are its inputs? I'm gonna have to pass some initial value for the parameters, which I'm gonna call x init. I'm gonna have to pass a number of iterations, so how many times do we optimize. I'm gonna need to use a learning rate. So actually, let me get this guy here so that it's more obvious what I'm doing. I'm gonna need a learning rate, I'm gonna need an interaction strength, I'm gonna need the interaction matrix, and the number of particles. I'm gonna need probably the dimensionality as well. So something like this. Okay, so then what we are going to do is we're going to loop over the number of iterations that we have. And again, because I'm not going to do it very efficiently, I'm also going to loop over all the particles, which you can avoid if you are smart and like vectorize things. But I'm not going to do it now because I just want the most simple version of the code. So the first thing that I'm going to need is the gradient. The gradient of our objective function, so this gradient of each of the fi's. Since each of the fi's is this quadratic, the gradient of it is basically going to equal this ai transpose times aix minus bi, something like that. So it's going to be, let me again copy this because I don't want to write it from scratch. Okay, so now I'm calling the particle iterator P, fine. So this is then this d by d, the pth d by d sub block of particle or node P. Oh, I'm gonna transpose this thing and multiply it by this thing itself. The particle that we're currently looking at, which is x, p, or how am I going to call it? So let's assume that this x init is of size number of particles by d. So I'm basically storing all of the parameters in this big matrix where each row is the xi. So row 1 is x1, x2, x3, and so it's going to be number of particles by the dimension of each of the individual parameters. So then here I'm going to use the bth row and all of the columns, because that should be the bth particle. And then again I'm going to subtract the b thing from our objective function, and then I need to change this to b. All right, so then I also need to initialize this x thing, so it's going to be a copy of the x init. So now we've defined the gradient. I guess that is correct, but also check it please, because again I make mistakes in these things. And then we're going to define our parameter update itself. So as I said, the parameter update is going to be like this. So the new iteration of x, I'm not going to store the x's in between, by the way, I'm just going to overwrite them. It's going to be the old one, again not the most efficient notation, but that's fine, minus the learning rate times the gradient, and then plus the interaction strength times this unit here. How am I going to define that? So my interaction matrix is an n by n thing. So if I multiply my interaction matrix with this matrix of particles, essentially what I should get is that each row of this matrix that we get, each row should be this thing. I think that is correct. So then we would have this. And then I need to select the bth row, because again we're interested in the A, B, J. And from this I'm going to have to also subtract the xi itself. So I'm going to subtract xp like this. I think this should be fine. Basically I'm updating it with a gradient step and an interaction step. Yeah, I guess it works. Yeah, we said we're not going to use any noise for now, can't be bothered. But you can add noise by just simulating a Gaussian normal, a sample from a normal distribution, and multiplying it by the noise variance sigma. So then what else am I going to do? I'm also going to store the loss, aka the value of the objective function. I'm going to have this train loss be a matrix of the number of iterations by the number of particles. So I'm basically going to store for each particle the value over time. So then train loss TP is going to be, what's it going to be? How did we define our thing? Like this, eval loss. Evaluated for particle P. And I think we would need to transpose this, because this guy is going to be 1 by d, and I think we needed it to be d by 1. Something like this. I might also need to transpose the gradient. I'm not sure, but let's see if it works. Okay, cool. Let's also print the train loss, and let's print it for, maybe not for each iteration, maybe for every 10th iteration. and then we return x and the train loss. Something like this, I guess. Let's find out if it is correct. All right, so we're gonna wanna run this unit. And the output is gonna be our one. I'm gonna, by the way, run it for 2 of the interaction matrices. So for the 1 and for the second one. This is gonna be x1 and x2. The first one was the circle graph, the second one was the fully connected graph. All right, then I need to define all these hyperparameters. So let's say the number of iterations. I don't know how many we will need. Let's say 1,000. For now, let's start with learning rate of 0.1. This guy, interaction strength, let's set it to 1, but let's see if that works. Number of particles we already defined. Interaction matrix we defined, and t we also defined. So then I just need to define the initialization. I'm just gonna do a random initialization, random standard normal. So number of particles by d, because that's the way I'm gonna initialize it. And then let's also try to plot these things. So what I wanna plot is the train loss over time. So I'm gonna use a range 0 to number of iterations, and I'm gonna plot the train loss of the first one just for the 0th particle. How did I define train loss? So I'm gonna use something like this, and then I'm gonna label this as circle, and then I'm gonna plot the same for the fully one, like this, and then I'm gonna show the legend, blah blah blah, left, so like that. Let's see if it works. Would be magical if it did, and it doesn't. Who is surprised? Could not broadcast input array from 5, 5 into shape 5. Okay. I don't know what that means. What have we done wrong? Maybe I need to be doing it like this. These guys should be fine. I'm not sure. No. Something in a gradient is not working. I need to transpose this maybe. Yes. Ooh, this looks pretty terrible. What have I done wrong? Maybe let's try a smaller learning rate. Still not fantastic. I don't know if this makes any sense. It does. Okay. I think it does. So the mistake was very small. Somehow I needed to have the x be 1 by d instead of just d. So let's see if the other guy also works. Kind of. Interesting. So they both converge to something like 11. Let me actually also plot the loss just above it so I don't have to scroll. The optimal loss is 9.99, if that one was correct. Let's see if I use a larger learning rate. So now, again, they both seem to converge pretty closely. The optimal loss, let me just print optimal so that we can see it. Okay, so the optimal loss is 10.6 and the fully connected one is converging to something like 10.6. And the other one, it's invisible because I should print here T as well. Otherwise, I don't know what's going on. So optimal is 10, fully connected one is converging to 10.98. And the circle graph is connecting to 11.00. Okay, this kind of shows what I wanted to show, which is that if we allow each of the particles to interact at every iteration, obviously they're going to converge kind of faster. The other thing that we can do to check actually what they actually converge to. So what I'm going to do is I'm just going to compute the distance between some of the particles. So for B in range, again, number of particles, I'm going to compute the distance norm of what? So I'm going to compute the L2 norm between the 0th particle and the bth particle. And I'm going to do the same for the second one. This should be a 1, this should be a 2, this should be a 2, and this should be distance 2. So I'm going to do the same for those, and then I'm going to print them. So I'm going to say circle is not very pretty output, but okay. And then the fully is the string distance 2. Okay, let's see if this works. Okay, so basically what we see is that this is actually strange. The distance for the circle is smaller than for the fully connected one, which is surprising because I would actually expect it to be the other way around. But they're both pretty small actually in this case. Let's see if we run it again, what happens. Okay, so in this case the fully connected one is smaller, but they're both actually pretty small. So what I've now computed with this distance is basically the L2 norm of the 0th particle to all the other particles in our network. And I want this to be small because I want all the particles to agree on their parameter value, aka I want the value of x1 to be the value of x2, to be the value of x3, and so on. So let's see what happens if I actually maybe change this EPS so I put more on the interaction and less on the gradient. Okay, then the circle does weird things. So let's not do that for now. Okay, so basically things seem to work okay. If I make the learning rate too high, then actually the fully connected one does a little bit worse even. Which could be the case. Let me actually do like this. So the circle graph needs a smaller interaction strength apparently, so I'm just gonna compare these two. So with these parameters, circle doesn't converge as well as the fully connected one does, which is also something that might be expected. Okay, I'm going to stop here, but basically as you see, the way you change the parameters, the learning rate and the interaction strength, it changes kind of what you converge to, which also makes sense if you were to look at the convergence proofs. So in essence, in this case, by the way, look at this, the distance between the circle the particle values for the circle is way higher than for the fully connected one, which also makes sense because we kind of put less weight on converging to consensus. But yeah, in essence, there's this trade-off between how much weight do we put on converging to consensus and how much weight do we put on the gradient steps. And depending on how we select it, you're going to converge to slightly different configurations. And in essence, fully connected might be better than a more sparse graph structure in terms of conversion speed, but obviously in terms of computational costs, in the fully connected one, we need to be exchanging at every iteration with all the particles, while for the circle, you're only exchanging for a few of your neighbors, in particular only one neighbor. So there's this trade-off again between also the sparsity of your graph and the total convergence speed. So I'm going to leave it here.